Hello friends, here is a quick review of titrations. We did the great majority of these problems in class already, but if it's helpful to listen to them again, I wanted to throw them out at you just in case. Our essential understanding for stoichiometry continues to be that the mole makes it possible to correlate the number of particles with the mass that can be measured. We're also going to look at how these moles react with each other, mole ratios, in balanced equations. Today we're going to focus on acid-base titrations and then redox titrations. We're going to talk about monoprotic versus diprotic acids. We'll define titrations. We'll do lots of calculations, have your calculators handy, looking at some solutions and titration data. And then we'll talk about, again, those acid-base titrations versus redox titrations. So let's say that I have a solution that has 2 moles of hydrochloric acid and we've got 2 moles of sodium hydroxide. What's super cool about this, because sodium hydroxide and hydrochloric acid are in this reaction in a 1-to-1 ratio, because I have this 1-to-1 ratio and because I have equal numbers of moles, 2 moles to 2 moles, these guys totally cancel each other out. So even though I started with acid and base, in the end, I just have some salt water. So these titrations are based on this neutralization of acids by bases or of bases by acids. This problem is a little bit more difficult because I don't just have equal numbers of moles on the page. Instead, we've got some more complex values. So we've got 12 cubic centimeters of 0.1 mole per cubic decimeter standard. NaOH standard in titrations just means that I know what its concentration is. So our known solution is our standard solution. Again, so we've got 12 cubic centimeters of this 0.10 mole per cubic decimeter standard sodium hydroxide, and I need that much to neutralize 25 cubic centimeters of an unknown concentration monoprotic acid. Monoprotic means that it has just one hydrogen. So protic or proton, remember that hydrogen ions are basically just protons. So if I'm talking about something like hydrochloric acid or hydrofluoric acid or nitric acid, these guys are all monoprotic because they have just one hydrogen. This makes it pretty easy because my one hydrogen in my acid and my one hydroxide in my base are going to make one water. So these guys are in a 1-to-1 ratio in my balanced equation. So I don't have to do too much in terms of railroad track stoichiometry. Instead, I can use a shortcut, M1V1, M2V2. We use this for dilutions. We can also use it with titrations if and only if I have equal numbers of OHs and H's in the 2 solutions that I am neutralizing each other with. So let's say that we need to finally do some math to deduce the concentration of the acid. We're going to do, here's our V1, the volume of the base. M1 is the molarity of the base, and then our V2 will be the volume of the acid, and then M2 is the concentration of that unknown acid, what we're going to solve for. So M1 V1 equals M2 V2. Why this works, remember that molarity is moles times cubic decimeters. If my volume is in cubic decimeters, +3, not -3, then when I multiply these guys, the dm3s and dm-3s cancel each other out. That happens on both sides. And so in the end, what I end up with is that the moles equal the moles, which works because I have 1 OH to 1 H. Those mole ratios are 1-to-1, so moles to moles works. We'll talk on the next slide about when it doesn't work because they don't match. But here, M1, V1, M2, V2. So M1 is 0.100 moles per cubic decimeter, and V1 is 12 cubic centimeters. Set that equal to M2 times V2 is 25 cubic centimeters. I do not have to convert my centimeters into decimeters here because I have cubic centimeters match and match, so they cancel each other out. I don't have to worry about converting. Divide both sides by 25 cubic centimeters. And we see here where cubic centimeters cancels out. What we're left with is 0.1 times 12 divided by 25. And I do need my calculator to do that. Looks like we get a grand total of 0.048. Unit label left is moles per cubic decimeter, because remember those centimeters cubed canceled out top and bottom. Moles times dm to the minus 3 is the molarity of my unknown acid. Good, good. Titration is the experimental technique that we use to get the data that we were just looking at. Again, standard solution is just our known solution. When we work in lab, we're going to try to find an unknown acid. So we'll put this in our flask under the burette. And in our burette, we will fill with that known sodium hydroxide, that 0.1 molar sodium hydroxide. If you had a known acid and an unknown base, you would just flip those guys. We're going to add phenolphthalein. Phenolphthalein is an acid-base indicator. It is pink in a base, and then it turns colorless in acid. So in the lab that we're going to do, we'll have our phenolphthalein with acid here in the flask. It will start colorless. As we add the base from the burette into the flask, then reactions will happen between the acid and the base. So there will be less and less and less acid in the flask because it'll be turning into salt water with our reaction between the sodium hydroxide and the acid. At some point, all of the acid in here will have reacted. All of it will now be salt water. And that one next drop of base that we add will cause that phenolphthalein to turn pink. That's when we stop. Except most of the time, we probably go a little too far. We almost always add too much the first time that we run our burette. And so we usually throw out the first trial. Usually the first trial is just, we'll figure out how close to get so that we know when to slow down super, super slow. In the second and third trials, throw out your first trial of data, which is weird because usually data are data. You never throw them out. But in this instance, we always throw out just the first trial. We're going to make things a little bit trickier here and look at a di-product titration. Di means 2, so now I have 2 H pluses in my acid. So same numbers that we started with in the last problem. I've got 12 cubic centimeters. I've got 0.100 moles per cubic decimeters of that standard known sodium hydroxide. And I still have 25 cubic centimeters of that acid, but this time it is sulfuric acid. Sulfuric acid is H2SO4. Diprotic because it's got 2 protons, 2 hydrogens. When I write the balanced equation for this guy, NaOH plus H2SO4 yields sodium sulfate and water. Sulfate's charge is a -2, sodium's a +1, so I need 2 sodiums to balance out that sulfate. I need 2 sodium hydroxides to balance the equation. I'm going to make 2 waters. I have a balanced equation, but notice that my mole ratio between sodium hydroxide and sulfuric acid is 2 to 1, not 1 to 1. It makes things just a little bit trickier. So what we're going to do is not use M1V1 equals M2V2. There is a way to do it, but you have to do some extra either doubling or dividing. So I'm going to start with railroad tracks because I think it makes more sense to get started. We're going to start with what we are given, 12 cubic centimeters of 0.100 moles per cubic decimeter. 12 centimeters cubed. Remember that of means multiply. Of means multiply 0.100 moles dm to the -3. So I'm going to go ahead and this time I do need to convert my cubic centimeters to cubic decimeters because I'm going to find moles from this little expression. Remember that to go from cubic centimeters to cubic decimeters, turn my C into a D, we divide by 1,000, 1, 2, 3 decimal places to the left. So 0.0120 cubic decimeters times 0.100 moles per cubic decimeters. So here, dm3 and dm-3 cancel each other out when we multiply, and we are left with 0.0120 times 0.1, which is just going to have us move our decimal place backward one more time, 0.00120. DM3, DM minus 3 canceled out. We're just left with moles of sodium hydroxide. Now we're going to go ahead and throw in our railroad tracks. 2 sodium hydroxides on the bottom, 1 sulfuric acid on the top will be my mole ratio here, and that's going to give me 0.00120 times 1 divided by 2, 0.000600, keep those 3 sig figs, moles of H2SO4. These number of moles of sulfuric acid are dissolved in 25 cubic centimeters. And so I'm just going to put my 25 cubic centimeters on the bottom. But of course, we know this has to be in cubic decimeters, so I'm going to divide by 1,000. 1, 2, 3, and turn that C into a D. My cat is playing with a toy in the background. I don't know if you can hear the bell. That's the cat. Sorry. Let's do this division. 0.000600 divided by 0.025 is going to give us a grand total of 0.024. Keep one more 0 for sig figs, moles per cubic decimeter of sulfuric acid. So here we have this titration. We're going to do a giant IB style question here. So ethane dioic acid is diprotic. It has 2 H's. We're going to figure out the value of X in the formula of the hydrated acid. This is kind of cool. The acid is a hydrate. So we're not looking for the concentration of the acid here, but instead we're looking to see how much water is attached to it. We're going to titrate it with a known mass of the acid, and we're going to use 0.100 moles per cubic decimeter of the sodium hydroxide solution. So here is our known mass. We're going to need this later, so definitely remember that this is here. We'll come looking for it in a little bit. We're going to dissolve that in distilled water so that our total volume is 250 cubic centimeters. We're going to then pull out little pieces to titrate. So I'm not titrating the whole thing all at once, but instead pulling out little aliquots that I'm going to use so I can do multiple trials. Titration was done 1 time. We throw out that data, and then we repeat 2 more. First question, IB is asking us about the uncertainty of the volume of sodium hydroxide added in cubic centimeters. So to find the sodium hydroxide, if my burette starts at 0 and I drip out until it's down to 13, 13 minus 0 is 13 cubic centimeters or milliliters of that sodium hydroxide. When we subtract our data, we add our uncertainties. So uncertainty for the volume of sodium hydroxide will be 0.05 plus 0.05 or plus or minus 0.10 in cubic centimeters. Calculate the average volume of sodium hydroxide using titrations 2 and 3 only because we throw out titration number 1. So here we're going to, again, subtract 25.7 minus 13 gives us 12.70. And in this one, we get 12.50. I can actually find that average in my head. Halfway between 5 and 7 is 6. So our average is going to be 12.60 plus or minus 0.10 cubic centimeters of sodium hydroxide. Now we want to figure out how many moles of this, how many moles is that equal to? So how many moles of sodium hydroxide in that volume of sodium hydroxide? To do that, we've got 12.60 cubic centimeters of means multiply, 0.100 moles per cubic decimeter. How do I know 0.100 moles? It's given to us right here in the problem. So what we're going to do is convert our cubic centimeters to cubic decimeters, turn that C into a D, and divide by 1,000. 1, 2, 3. So 0.01260 cubic decimeters times 0.100 moles per cubic decimeter. So what happens here, of course, is my DM3 and DM minus 3 cancel out. We're left with moles, which is exactly what my question asked me to find. This is easy math. Multiply by 0.1 means we're going to move that decimal place backwards just one more time. So we end up with 0.001260 moles of sodium hydroxide. Hold on to that number. We're going to need it on the next page, 0.001260. All right, so I have added here some of the numbers that we had from the previous slide, just so we don't have to keep clicking back and forth in the video. So we just determined that there were 0.001260 moles of sodium hydroxide in each trial, in each titration trial. We're going to first figure out the amount in moles of ethane dioic acid that reacted with that average volume. That was our number of moles in those average volumes of sodium hydroxide. So super easy, we're just going to take those moles of sodium hydroxide and use the mole ratio from our balanced equation, 2 NaOHs to every 1 ethane dioic acid. And that's going to give us 0.006300 with my 4 sig figs moles of HOOCCOOH for each of those trials. Good? Good. So that's part I. Part I asks us how many moles of that ethane dioic acid in the whole 250 cubic centimeters that we made up at the start of the problem. Remember that on the previous slide, we put our 0.795 grams of ethane dioic acid into 250 cubic centimeters total, and then we pulled out 25 cubic centimeters for each trial. So this is how many moles reacted from 25 cubic centimeters. How much in my original whole 250 cubic centimeters? This is easy. We're just going to multiply by 10. So we will take our 0.006300 moles of HOOCCOOH in 25 cubic centimeters and multiply it by 10 to get there's a decimal point in there, 0.006300 moles in 250 cubic centimeters. Now we need to figure out the molar mass. So remember that from the previous slide, we added 0.795 grams, and I see here that we have 0.006300 moles in 250 cubic centimeters. So if I do molar mass, remember that molar mass is grams per mole. If I take my grams, again, this was given to me in the question on the previous slide, 0.795 grams, and divide that by the number of moles that we just figured out, 0.006300 moles, then my molar mass in grams per mole is easy peasy division. 0.795 divided by 0.006300 gives us 126 actually I'm going to stop there, 126 grams per mole, because I'm going to keep only 3 sig figs, is the molar mass of the hydrated ethane dioic acid, the stuff that I originally started with. So now we're being asked to figure out how much water is there. How do I figure out X given the molar mass of the hydrated ethane dioic acid? How could I figure out how much water is there? We're just going to subtract the mass of the ethane dioic acid from the hydrated ethane dioic acid, and then we'll know how much water is there. So part 4, little IV, we're going to take 126 grams per mole, the hydrated version. I'm going to subtract the mass of the unhydrated. So HOOCCOOH, I've got 2 carbons, 2 times 12 is 24. I have 2 hydrogens times 2, that's 26. 26 plus 1, 2, 3, 4, 4 times 16 is 48. No, that's wrong, 64. 64 plus 12 plus 2 gives me a grand total of, oh wait, there's 2 12s, sorry, 90 grams per mole. Sorry, that was rough mental math. I should have used my calculator. 90 grams per mole is the just HOOC-COOH. So I found just the mass of HOOC-COOH, the anhydrous, not hydrated ethane dioic acid. So when I do this subtraction, hydrated minus not hydrated, the only mass I have left, those 36 grams per mole, is water. And we know that water is 18 grams per mole. So we must have 2 moles of water on every one of those ethane dioic acid molecules, which means that X is equal to 2. Good? Good. Here we're going to look at one more giant problem. We're going to do redox titration this time. The last problem that we looked at was acid-base titration. We used an acid-base indicator. Phenolphthalein was the one that we often used, the one that was used in the problem on the previous page. Phenolphthalein is pink in a base and colorless in an acid, and that color change allows us to know when all the acid has been neutralized, all the base has been neutralized. In this redox titration, we don't have acids and bases, so we can't really use an acid-base indicator. Instead, we're going to use a very colorful oxidizing or reducing agent. So this guy, potassium permanganate, the manganese ion here is a +7. It is going to be reduced to manganese +2. The +7 is super, super purple. So purple. And then the +2 is colorless. And so we'll see in our setup, pardon my art skills here. So we're going to put our unknown in here. Our unknown is going to be some iron sulfate. We're going to add some acid just to help prevent the iron and the manganese from being combined with oxygen and turning it into super gunky stuff. So we've got our iron in here. That iron is going to go from +2 to +3. It's going to be oxidized as the manganese is reduced. So it will be colorless and we'll have purple, purple, purple. Let me actually make it purple. It'll be purple, purple, purple. And then that purple will drip down. And when the purple hits here with the iron, that reaction happens and the purple will become colorless. And then we add some more purple and the reaction happens and it's flipped to colorless because our 7+ is going to 2+. At some point though, all of the Fe+2 will be Fe+3. And so that last drip of potassium permanganate, there isn't any more of this to turn that into that. And so it stays purple. And so the whole thing turns a very pale purple pink color, and we know that we are done. So what we're going to do is look at 1.65 grams of iron tablets that are ground up and dissolved in 100 cubic centimeters of sulfuric acid. We are going to take aliquots 25 cubic centimeters of the iron and use that into a conical flask, which is the same thing as Erlenmeyer. And then we're going to carry out the titration. We're going to use 5 times 10 to the -3 mole per cubic decimeter standard solution. Again, standard just means that we know the concentration of it, potassium permanganate. So hold on to all of these details and let's do some math. Since we're here, we might as well do a quick little bit of a redox review. Remember that reduction, Leo says GR, in terms of electrons, it is a gain of electrons. The oxidation number of manganese in MnO4, that permanganate ion. So oxygen is a -2. -2 times 4 is -8. I want to keep a -1. So this guy is that +7 charge on the manganese ion. So finally here we're going to do our math. We're going to take these results from the titrations. We're going to use this balanced equation to first determine the amount in moles of permanganate ion used in each accurate titer. So this one's kind of interesting. They didn't even give us like trial 1, 2, 3. They just said this one's the rough one, throw it out. We're going to use the first and second accurate titers, trials 2 and 3. To do that, I'm going to go ahead and subtract my 18 minus 1.20. That's going to give me 16.80 here. Subtract, we've got 16.80 again. I don't even have to calculate averages because those are the same numbers. So we're going to take our 16.80 cubic centimeters of, remember that of means multiply, our, from the previous slide said 5.00 times 10 to the minus 3 moles per cubic decimeter was the concentration of our permanganate. So I'm going to turn my CM3s into DM3s by dividing by 1,000. 1, 2, 3, so 0.01680 times 5 times 10 to the minus 3. Calculator says 8.4. I'm going to keep one more sig fig, times 10 to the minus 5 moles of MnO4 minus 1 charge. That's because when I multiply dm positive 3 by dm minus 3, they cancel out. So here is our answer to the first part of the problem. Next, I want to figure out how many moles of iron we used in the 250 cubic centimeter solution. So I'm going to start by using my mole ratios, the moles that I have here, and my mole ratios. So 8.40 times 10 to the minus 5 moles of MnO4 minus 1 charge that we found from part F. And then railroad track that. Put my 1 MnO4 minus on the bottom and my 5 Fe2 pluses on the top. My manganese top and bottom will cancel out, and 8.4 times 10 to the minus 5 times 5 gives us, calculator says, 4.20 times 10 to the minus 4 moles of Fe2 plus. But that's for each one of my titers, and we used 25 cubic centimeters of the solution that I pulled out of the original 250. So this is for each 25. To get all of it that I had in the original 250, we're going to multiply by 10. So that's going to give us 4.2. I'm going to keep just 2 sig figs this time since I have this 250 in here, times 10 to the minus 3 moles of Fe2 plus in my 250 cubic centimeters. This was only in 25 cubic centimeters. So far, so good. All right, so now let's figure out the mass of the iron that we have in those 250 cubic centimeters. That's super easy. We've got moles. We want to convert to grams. Basic stoichiometry. We've got 4.2 times 10 to the minus 3 moles of iron. I want to get rid of moles, turn my moles into grams. Moles on the bottom, grams on the top. Periodic table says that there are 55.85 grams in 1 mole of iron. So if I take my 4.2 times 10 to the minus 3 and I multiply by 55.85, I have 0.23457. I'm just going to keep 2 sig figs, so 0.23 grams of iron. So now I need to figure out the percent by mass of iron in the tablets. On the previous slide, we were told that the whole tablet was 1.65 grams. So if I have 0.23 grams of iron and the whole thing is 1.65 grams, multiply that by 100 to turn it into a percentage, and 0.23 divided by 1.65 gives us a grand total of 13.9, we'll round that to 14% iron in the tablets. And on that note, we did it. We talked about monoprotic and diprotic acids. HCl is an example of a monoprotic acid. It just has 1 proton, 1 hydrogen. Diprotic would be something like H2SO4 because it has two hydrogens, 2 protons. We talked about titration, that experimental technique for us to figure out the solutions of unknown, or the concentrations rather, of unknown solutions. We did some math with some titration data. We talked about both acid-base titrations and redox titrations. Both of them require a color change to let us know that we're done. Great work today, my friends.